Matt, I believe.
Great. So I'm just sharing a screen. Hopefully that's come up. I'm going to give an overview of the technology. We've got an unboxing video that we'll show, and then we'll get into some more details. Hopefully we'll leave the most time for Q&A, because hopefully that's where we can get a lot of the value for you guys watching. So I'm going to introduce the technology. It's a new generation of chemical sensors that we've developed for all water environments, so very robust technology with a lot of different applications. So I'm going to take you through that just now. I can get it to advance the slide. There we go. Okay, so what's the problem that we're addressing? Well, it's this need for high quality and convenient chemistry data. The drivers include things like urbanization, population growth, and environmental change for a lot of reasons, not least climate change. And as coming from the science community, our science users and increasingly stakeholders in industry were expressing to us that it was problematic and not great to be doing infrequent and relatively expensive manual sampling that was often missing temporal and spatial variations, not able to really measure the chemistry in the sort of required resolution that they needed. And that the current sensors were either a bit fragile, didn't have sufficient performance, or measured proxies, things like fluorescence that aren't necessarily directly related to the chemistry, and some of the the better sensors were in sizable boxes that had to go by the side of the water or in air on a vehicle or something, and they were not ideal because they would get vandalized, they'd freeze in cold weathers, and they'd overheat in hot weathers, and also there was a relatively costly way of doing it, which led those users to not being able to make informed decisions or scientific conclusions because the lack of high quality data they could get. So we came up with this technology over a number of years. I'm going to give you a quick tour of the history of it in a moment, but it's an in situ sensor, so it can be deployed directly in the environment, and gives what we like to say is no compromise real-time water quality monitoring. It's lab quality data, uses principles very similar to a standard auto analyzer, wet chemistry reagent-based methods, very, very high performance. And one of the nice things that we can do, because it's that method, we can carry on board standards and blanks, and we can bracket measurements or occasionally calibrate the instrument to eliminate drift. And because it's using these industry standard reagent methods that we've adapted to work on lab on chip, interferences are very well understood and really minimized. It can go in any water environment for several months, and we've rated it to 6,000 meters depth. We've got 5 variants of it: a nitrate sensor, a phosphate sensor, silicate sensor, ion sensor, and a pH sensor, and they're all targeting that really high quality measurement. One of the nice things that the technology allows us to do is to have multiple absorption cells. And for example, in the nitrate instrument, that gives us a very wide range of concentrations that we can look at. I'll come to that in a minute. We've done quite well. So we started actually shipping sensors in early 2021. And since then, we've grown purely through sales and our own turnover. We've had a little bit of grant income, but our seed investment we haven't added to yet. And we've had customers in government, a number of monitoring organizations, some doing actual statutory monitoring, but some significant sizes of programs. We've had a lot of science customers, both in oceans and in terrestrial applications, things like catchments. A few people who have been integrating them with autonomous vehicles. We make that as easy as we can. That's kind of our alma mater. We grew up doing that, and there are some tools for integrating the sensors into vehicles. And recently, we've been doing a lot in the sort of CDR, carbon dioxide removal market, and been involved with a project that's at scale-up phase. It's really exciting, looking at doing very large-scale CDR type deployments. The technology, not least because it's developed for such a long time in the National Oceanography Centre, is very well proven. It's done well over now 200 deployments. and we can send anybody who's interested a long list of publications based on those deployments and that technology. The applications that we're seeing currently are things like catchment monitoring. It's very nice because minimal infrastructure is required. We typically deploy with a solar panel and a battery and the device. Quite a bit in terrestrial and industrial water quality management and assurance, including with water utilities in the UK, the companies that run waste and drinking water. Significant number of oceanographic, scientific and biochemists users taking the sensors, regulatory monitoring. Aquaculture is a big growth area, quite difficult for us to get into, but actually is a significant market. There's a lot of interest there. Subsea carbon storage monitoring. We had a big project through the NOC called STEM CCS. Did a lot of that, and that's resulted in us getting now commercial scale applications of that, and as I mentioned, carbon dioxide removal. So the history, this idea has been around for a long time. So we're certainly not the first group to look at reagent-based monitoring of chemistry, but the use of lab on chip was an idea that was developed back in about 2002. So that's 22 years ago. And since then, there's been a number of projects. In all, actually, it's nearer 30 million in UK funding to get this technology where it was up to the state it is today. And latterly, since about 2011, we have also very good, 2 screens, and we have lately had a lot of investment to allow us to come to commercial scale. I think everybody involved was keen that this technology didn't sit in academia and was out there doing some good in the world with other wider stakeholders. So there's been a lot of fun, but a long history in getting the technology to the state it's at today. I mentioned that we do a fair amount, or have done a fair amount, of integration into vehicles. So a lot of this work has been done by colleagues in the National Oceanography Centre in the NOC. So here's some data actually by colleagues at University of East Anglia in the UK, measuring pH with this very precise reagent-based method, indicator dye-based method from a glider, and it was running up against electrochemical methods and did very well, produced much better data. So that's what we've all integrated this onto the Kongsberg Sea Glider, the Surface Vehicle Autonaut, and also the Sea Explorer glider. And we've got lots of examples that we can show you. And the nice thing is we've got software and communication protocols that make that integration relatively easy. The technology does work in extreme environments. So you can see Alex there putting the device into a proglacial melt stream. You can see it's pretty high in turbidity. There's a lot of ice in it, obviously very low temperature. So he's got some nice data sets showing low temperature operation. The year-long deployment that was mentioned in the intro was actually in ice-covered Arctic Sea. So it can deal with these very low concentrations as well as high concentrations in some of the variants. I'll come to that. Okay, so here's the sort of details of the performance. So you can see that very wide concentration range of particularly the nitrate instrument. It's got a detection limit down in the low nanomolar, so 25 nanomoles, 0.025 micromolar, and from that sort of concentration up until to the millimolar, 1,000 micromolar range. And there's the specs for the other devices. We can do special assays. Obviously, that incurs a bit more time. But for example, we're currently able, on request, to do a high concentration phosphate range. That does need a bit of R&D and just checking what the water quality and matrix is that in your test area. So if you're interested in higher concentration ranges than are shown here, then please do get in touch and we'll try and address that. Okay, so what are we looking for? Well, always up for new customers, but partners as well who want to test and look at applications and projects, particularly through Aquatic Sensors. looking at applications and developments that we can do to better suit your need. So in summary, we've got a new generation of chemical sensors, which are high performance, no compromise on the data quality. They're robust and proven, suitable for unattended operations, and can be integrated into autonomous platforms and observing systems. And there's lots of applications. It's great finding out new ones all the time. So please do get in touch to discuss. I'll stop there and I will hand over to Alex.
Great. And if I can just interrupt, sorry. Thanks, Matt. That was great. Alex, are you able to unmute, and Adrian can mute? Can you flip that? Just because when you talk, we end up seeing Adrian's camera. So just wanted if you can't, that's fine. We'll just turn the.
Yeah, we can try that.
You'll have to turn your speaker on though, Alex. Oh no. Oh no. Oh no.
World-class sensors, microphone 0. Yeah.
Okay, I think we sorted that out. Can you hear me now? Okay.
You bet.
Good. I don't need these anymore. Okay, so Matt's given a quick intro. I'm just going to show a short video, which is sort of an unboxing video. It definitely doesn't contain all the details we're going to get into in the Q&A, but it sort of gives an idea of the sort of what the sensor looks like and how you set it up as well. So let me just share my screen. So hopefully this has got audio. So if you can't hear anything, let me know. But it's going to start with a bit of music, and then it will be me sort of unboxing the sensor. So I'll fire away now.
Just a comment, Alex, we can't hear anything, so you might have to go down into your more or your audio and share audio down in the toolbar.
In Zoom or here?
In Zoom. Yeah, it's a
yeah.
Zoom thing.
Okay.
Thank you.
More. Oh yeah, share sound. Okay. I'll try that again.
So today we're looking at the ClearWater Sensors lab-on-chip chemical sensors. We're going to take it out of the box and take a look at it. So this is the box it ships in. We'll just open it up. And inside we have the sensor itself, which is here. We've also got a lab cable and a box of accessories. So the lab cable connects to the cable coming out of the top of the sensor, and it breaks out into a USB cable that can be plugged into the computer for setting up the sensor, 2 power leads, and a DB9 serial cable, which can be used for testing the serial port. So to remove the reagent canister, first we're going to disconnect the cable. We're then going to use our tool to unscrew 3 screws under here. this locking ring will drop away and allow us to lift up the reagent canister. So this is now removed. Underneath, we can see the connectors. This canister can be refilled, or it can be sent back to ClearWater Sensors for refill. So we're going to plug our cables into our power supply, which we've got set to about 12 volts. We've got a USB cable plugged into our computer, and we're going to open the Windows-based GUI, which will allow us to talk to the sensor and set it up for deployment. So when we plug the USB cable in, the sensor will appear in the GUI. We can double click on it, and we're now connected to the sensor. The first thing we're going to do is prime the filter. This stops the filter being dry and means it's able to draw in a sample. So we're going to select prime and click start. We need to make sure that the sensor has its 12 volt power supply. So it's currently powered via the USB port, but in order to actually run the sensor, we need to make sure it has 12 volts. So if you don't have 12 the power, then it will tell you. So I have applied power and press start. So now it is pumping a very small amount of blank solution into the filter to prime it. It's important to do this before running sensor. So once we prime the filter, we can configure the settings of the sensor. So we can make sure we've got our real-time clock adjusted to the time zone we're working in. We can make sure that our RS-232 is set up correctly. So we can set it to either polling mode or streaming mode. And we can set our measurement scheduler. So this allows us to schedule how often the measurements happen. So in time series mode, the nitrate sensor can run approximately every 20 minutes for a fully calibrated measurement. But we can reduce that by setting it to run every hour or every 2 hours, or whatever interval you require. We can also program in a stop time, which will enable us to set a time when the sensor will automatically stop measuring if we've got a deployment that or a sensor that we need to recover at a certain time. We've also got, we can also set a start time, which will mean that the sensor won't start until that time. It's important to test the sensor when you first receive it. So we recommend priming the filter and then connecting an inlet tube to the filter and running some measurements of some fluids to check that we're getting sensible measurements. We can view the output in various formats. So we can either look at the raw data in a graph here from the various different channels. We can also look at the processed output either as a graph or as text. And the processed output text shows us the concentration value from 3 different channels, as well as the date, the timestamp, once the sensor has been set up using the lab cable and you're ready to deploy it, the lab cable needs to be removed, and when at the field site we can connect to our deployment cable. So this will be generally a longer cable that we will connect, and this will plug into a power supply or a logger or whatever platform you want to connect the sensor to.
Okay, so that was just a short unboxing video. I just wanted to clarify. So that's just the setup of one of the sensors. The interface is the same for all of them in the range that we've got at the moment. So it's very similar for each of the parameters. That just happened to be a nitrate sensor, but there were a couple of other sensors on the desk at the same time. And I think what we're going to do now is sort of try. Well, I'll hand back to you, Andrea, because I think we're going to go into Q&A. Unless you've got anything else you wanted to add, Matt.
I think let's go to Q&A. I see some popped up in the chat.
Yeah.
Andrea, if you want to take the chair, that'd be great.
Yeah.
Absolutely, absolutely. Okay, yeah. So let's just. Oh, sorry.
No, I was just going to say, I just realized I'm wearing exactly the same thing as I was when we recorded that video.
That's because you made it today.
Yeah, yesterday.
Okay.
Even worse.
That's okay. Thank you for sharing. Okay, I'm just going to start from the top because they kind of progress really nicely. So the first one from Anya is, how often do these sensors have to be serviced during like a 12-month deployment if they're out for a year?
Do you want me to take that?
Yeah.
So the servicing we recommend is done once a year or after 4,000. So that's the servicing itself, but it's worth saying it depends how frequently you're making measurements as to how frequently you would have to make reagent pack changes to make sure that you have fresh reagents. In cold environments, also, reagent lifetime isn't so much of an issue, but in warmer environments, we'd recommend changing out the reagent pack every 3 months. So we find that the combination of those factors mean that many customers will swap out reagent packs every 3 months and then go for an annual service, and they'll typically run at sort of hour to 2 hour measurement frequency to fit in with that schedule. We do have some customers that run them full chat, measurement every 5 or 8 minutes, depending on the variant, and then they will need more regular reagent packs. But yes, there's about 1,000 measurements in most of the nutrient packs, and depending on how you deal with the waste, either 1,500 or 3,000 measurements in the pH measurement pack. So you can work out the duration that you've got from how long the reagents last. Having said that, some devices have stayed out for the whole year making nutrient measurements in cold environments if the timing is set correctly.
Exactly. Okay, and I think I know Alex said you can send the cartridge back, but you also can just order the bags separately and put them in the existing cartridge as well.
Yeah, you can order. We can supply them in bottles that can be refilled into the cartridge. Yeah, so you can basically you can do the refill.
We can do the refill twice. Awesome. Okay, so who wants to take this one? What is your trick for monitoring in environments with high sediment loads?
Yeah, good question. So because it's a microfluidic system, it uses quite a low volume of sample. So that puts us in quite a good position to start with. So it's not passing that much fluid through the filter. But because we're trying to make scientific quality measurements, we're using a 0.45 micron inlet filter, which then means, okay, it's not going to it's going to block more frequently than maybe a larger pore size filter. Typically in ocean environments, you don't need to do a filter change more frequently than a reagent change. In some very turbid rivers, we have found sometimes there has to be a filter change sort of mid cartridge. You might have to visit after 500 measurements or something just to do that. but that's only in the sort of the very turbid environments. We're looking at actually to try and address that, looking at a pre-filter as well. But at present, in some very turbid environments, you might have to swap the filter earlier than the reagents. And I say that because normally the reagents is the sort of, you know, the reason you'd have to visit the site to attend to the sensor. In some cases, you might have to do a more frequent visit for the filter.
Okay, so I'm just gonna keep on the theme of like performance in certain environments, because we have a question. It says, so how well does this instrument perform in riverine environments? And the USG office has worked with similar wet chemistry phosphate instruments and found that the sediment load in the river clogged the filters and made the instrument nearly inoperable.
Yeah, so I think that's related to the volume of water intake through the filter. So I suspect I know which phosphate instrument that was, and that needed a lot of sample water to flush the instrument between measurements. So some of the other instruments on the market can take tens of milliliters. I think one of them is about 50 milliliters of sample per measurement to flush the instrument, whereas we're talking more like half a milliliter. So a really big difference in how much is being used. You give me a better number if you want, Alec.
No.
Yeah. So is that big difference in scale in the quantity of water that's required to flush the instrument means that the filters tend to last much longer. Alex is right. You know, in very turbid environments, we may need to suggest a pre-filter, or that you swap the current filter more regularly than the reagent pack. But it will still be of the order of several hundred measurements before that filter needs changing.
Okay, I'm keeping on the sediment question here. I'm just going to skip a few and tie them all in. So in addition to the sediments, what are other possible sources of interference? Some nitrate sensors are challenged in inland water settings.
Yes, so we're using the reagent-based method, and so there are some interference fairly well published between some of the assays. So, for example, the phosphate assay has a slight silicate interference, but we've done some work to minimize those things. The pH sensor may detect real pH changes, but due to biofouling, so that may be different to the environment, but we've only seen that in very few measurement systems. Because those relatively small interference are known and can be accounted for. Alex, I don't know if you want to mention any others, really.
No, I don't think so.
Yeah, and so vice versa, the silicate assay can sometimes be a little bit phosphate sensitive. But again, if we know your matrix, your environment, we can help with that, and we've done a lot of work to minimize that already.
Okay, I think yeah, that's, if anybody has any other sediment type questions, please pop them in. Except for, what has been your experience with fouling, especially in high productivity waters?
Yeah, so there will be growth over the sensor housing, of course, in high fouling environments. We haven't had any problems with these sensors in terms of biofouling. I think if something literally grows over the sample inlet, then that would be a problem. But generally, we haven't had reports of that. I think on earlier prototypes we did have issues with stuff growing in the we had an issue with crabs living in the reagent canister, but we've managed to redesign it so that doesn't happen. And there's, you know, there will be a lot, they come out of the water looking awful because they're covered in growth, but generally we haven't had reports of poor operation due to fouling, at least. I think that's what we can say.
Yeah,
Go ahead.
The benchmarking measurements that we've made in high fouling environments, only in the case of the pH sensor when there was literally algae living in and on top of the filter, and they were actually respiring and therefore changing pH. We've not seen any interference because between the co-sample benchmarking measurements and the sensor outputs because of fouling.
And I kind of, would you also say, I don't know if anybody has an instrument on their hand where they can show where actually the sip of water needs to be taken, because it's such a small sip of water that it's not it's not a large amount that you need to push through the microfluidics to get a sample. So it gives you a good idea of just a small quantity of what you need to actually get a good sample. So yeah,
so
that would be
there
like,
is an inlet without the filter fitted, but you can see it's the standard lure lock fitting, and on the device that's got the Adrian's just bringing one over with the reagent canister, and you can see there's a standard. It's a syringe-based polysulfone filter that just fits onto that lure lock fitting, and you can see it's very small, and that's when I first started this, that's what I thought would kill all microfluidics, is the particles, but actually you need a very, very small capacity filter. The small filters are better in some regards because they need less flushing, because you get a representative sample more quickly. If you put a bigger filter on, it actually needs more flushing and can clog faster. So there's a optimum there, and for most of the deployments, that size filter is what you need.
awesome. Okay, switching gears a little, who would like to answer, what is the accuracy of the sensors compared to certified reference materials?
Yeah, good question. So we do run a CRM, certified reference material, on the sensors before they go out the door, and we look for an accuracy better than 0.2 micromolar, but normally it's better than that. But that it very much depends on the because it references the onboard standard regularly, so that is really that's the sort of benchmark we're going against. So as long as that is accurate and has been prepared accurately in our labs, then the sensor should read accurately, and that is tested before they go out the door. So we use at least for the seawater, so we use Kanso CRMs for the sensors that are set up for seawater operation, and then we use another reference material for freshwater. But yeah, they are tested against the CRM before they're released.
Yeah, so the key thing on accuracy is do the onboard standards hold their value. We do some preservation techniques on the standards that are held, and as long as that's true, actually the accuracy stays very close to the instrument precision, and the precision we like to see the sensors have is a few percent at worst, and typically 1 or 2% across the range, and so they should stay within that sort of value compared to the onboard standards. And those onboard standards typically are pretty robust. We do some preservatives on them. We do recommend, though, that when you retrieve the instrument, you try and take if you want to monitor the drift, you do take a sample of the onboard standard and blank, and then we can verify whether those have drifted during the deployment. It's a bit of extra metrology certainty.
Okay, great. Yeah, I know one of the questions was what was the seawater CRM used, and Alex said it's Kanso CRMs, CANSO. So thank you for that. And also just they're looking for what the accuracy of pH is. So can you comment on the pH accuracy outside of 7.5 to 8.5 range?
So once it starts to get out of that range, I think we should have a discussion, because you really would be advised to look at a different dye system than our standard dye. So we use a single dye. Currently, they're all set up to run metacresol purple, MCP, and so its pKa means that it's happy around 8.1. That's its optimum sensitivity. As you go out beyond that, however, we have calibrated up to about pH 9, and the accuracy at somewhere nice in the range is 6 to 9 milli-pH accuracy, probably near a 9 in most circumstances. Once you start getting up to pH 9. It's going to be worse than that. I don't have the figure in mind, but I know once you're getting up to the sort of 8.5, we can be down to sort of 14 millipH accuracy. So you can see the progression, and it's a sigmoidal curve, so it tends to roll up. It is possible, and I've got a couple of papers on it, to do multiple dyes or use different dyes with pKa's to extend that range. And so if you want range over accuracy, I would recommend that we have a discussion on that. But as standard, yeah, we would say 7.5 to 8.5 is the best range for that dye.
Okay. All right. Thanks, Mallory. If you have any more questions about that, if you guys want to actually even ask further questions, we'll get you Matt and Alex and Adrian's contact details. So further to more questions, there was one more interference one I kind of missed. It was, is there any from high FDOM, CDOM environments? So like,
You want to take that because I'm just answering a
yeah,
typing.
type, so I'll take that. So fluorescence has very little effect on the sensor because we do a referenced absorption measurement, so it's not particularly sensitive to fluorescence. The coloured dissolved organic matter does have absorbance at our analytical wavelengths, but because we do the way in which we do our measurements does allow us to remove that effect. So we effectively do a sample blank, and so we can look at the native absorption of the material before we do the analytical determination. And so the effects of CDOM and FDOM are not great. There may be small effects on the precision, but on accuracy, we typically don't have that problem.
okay, thanks, Matt. What is the limit of detection in milligrams per liter for phosphate?
That's a good question. I being an
Should
old
we get the chart out? Should we get the chart out?
Yeah, you might have to get the chart out. I can't remember off the top of my head.
Okay, let us get back to you on that one. We do have a conversion rate for that one. So like we'll put a pin in that one for now. So there was a few more questions, just more about kind of the operational procedures. So is this compatible with Linux OS? Did I say that right? Linux or Linux? I don't know how you,
Linux,
the British.
OS.
Operating
I have
system
to
is
take
Linux,
that one
yeah.
back. I'm not sure. We certainly do have, you know, the actual interface is based on a standard RS-232 protocol, which has operated over Linux. I'm just wondering whether our GUI drivers have also got a Linux version. I think not. I think not at this stage.
No, so the GUI, the thing I was sort of going through in the video on the screen, that's the GUI, which is, it only works in Windows, unfortunately, but it's used for setting up, adjusting various settings with a graphical user interface. And then we've also got an RS-232 connection, which is how it would talk to a machine, so a logger or, you know, a platform or something like that. And that could be, you know, configured to talk to most devices. Now, the GUI only works in Windows, but the serial connection, which is where it would transmit the processed data output, and it can also receive a limited number of commands via the serial port as well. So you can tell it to sample and to flush and things over the serial. That obviously that can just that's a pretty standard interface, so it can be connected to lots of devices.
Like a terminal emulator, or only through software?
Yeah, so you can use the terminal emulator to set it up. A lot of people do that. It is designed to talk to machines. You do need to copy and paste commands into the terminal emulator rather than typing them. Is one thing that some people have noticed. But you can use something like, you know, Teraterm or to send commands just to sort of test that interface and get it working. But generally, you would then have a device that sends those commands automatically in the field.
Okay, let me just take a peek here. What else? Is this sensor the type that receives power from the ship via power cable? So can you Can you run it also, I guess, to do maybe, deployments, profiles, that sort of thing? I'm assuming, I'm not sure what the application is. It's just wondering if you can run it from a power cable from a ship. Have you done that before?
To some extent, yes. I mean, so to be clear, the sensor, it doesn't have a built-in battery, mostly because the range of deployments it's capable of is so diverse that having a one-size-fits-all battery isn't really a sensible thing. So it does need a power supply. In sort of ocean deployments, if it's a shallow one, it may be via a cable, or it might be powered from the C to D frame, for example. That could be set up to do that. But generally, it might have a deep sea battery pack attached to it for those sorts of deployments. But it basically needs a 12-volt supply, whether that's a battery or comes directly from the ship. It just depends on the deployment scenario.
For sure. I mean, and you've really designed these to be left remote in the field for long periods of time, whether you run them off a solar panel battery or
lots of deployment scenarios. So we've got lots of customers who are working in sort of inland waterways and rivers and stuff, and generally in that situation, a solar charged battery is the best solution, and we do supply a small box with a battery and a panel for customers if they want to do that, although sometimes they've already got that sort of that sort of infrastructure. And then for things like coastal moorings with surface expressions, it might be powered via solar panels there as well. But for sort of deep sea applications, generally it would be a sort of deep sea power pack. So for example, the sort of year-long deep sea deployments that have been done have all been batteries, lithium primary batteries in deep sea casings, basically to power the sensor that way. But yeah, we don't supply a one-size-fits-all battery, but we can certainly advise on what we think would be the best way to power the sensor.
And in terms of connecting to things, so we have in the NOC connected this sensor to CTD rosettes and broken out from the power supply there, and also Toyo seesaw type vehicles being towed behind ships with cables. So it's all possible, and we can help with some of the details on how to enable that.
For sure. And you've actually even taken the reagents out of the canister to make them fit into vehicles. So it's very flexible.
Yeah, I suppose that's worth mentioning. So the sensor that you see in the photos and the one that we showed in the video, that is the setup that we supply to most of our customers, but we do have a special vehicle version of it that we've supplied to some customers who've integrated them into gliders and AUVs, and that's where maybe the full reagent canister setup doesn't fit, but we can supply a system where the bags are sort of are not in that reagent canister. The reagent's stored in bags, which can be stowed in the vehicle. So the stuff we've done with sea gliders and some AUVs have been done like that as well.
Okay, yeah, that's worth a mention for sure. Thanks, Alex. Okay, so I just want to get to Tamara, if I sent your name right. She's asked 2 questions, so I'm going to start with her second question. Any experience deploying in estuaries, collecting data every 15 minutes? And can you comment on the drift over time that has been observed? Hang on here, we can break this down. I'm just going to read it all at first. If so, is it linear or stepwise? And how do you recommend users to determine and account for this drift? So collection data every 15 minutes in estuaries and drift.
We have deployed in estuaries a number of times. I'm not sure we've gone as fast as 15 minutes, but the sensor can. So I'm just trying to think back to some of the estuarine deployments that we've done. I think they've been more like half hour or hour, looking at tidal cycles. There's no reason why you couldn't go for that sort of frequency. In terms of drift, then we wouldn't expect to see drift in that environment because we're carrying the onboard standards. You may see some if you slow down the calibrations, if you perhaps did more measurements than calibrations, there may be an element of drift, but I don't. That tends to not be that significant, actually. The sort of instrumental drift between the calibrations. So yeah, yes, we've done extra own work, not 15 minutes, but drift isn't really the issue that we would worry about.
And is there anything sorry, go ahead, Alex. Yeah.
No, go on. I think you were going to say what I was going to say. So
I'm not sure. I know she was just talking about stepwise and the other kind of drift, but basically there really isn't a lot of drift if you're looking at it a half an hour to an hour. So to speak.
yeah, and you can sample the onboard. It will be related to the onboard standard, so you can sample that at the end for your own sort of peace of mind to check that hasn't drifted. So then you can get that analyzed, and then you'll be sure. But it should within those sorts of timescales, it should be okay.
Okay, and then just related to that, because I think she works in estuary waters. What's her method? What's the method reference for ammonia and phosphate?
Okay, so ammonia is not
Ammonium. Sorry, ammonium. Yeah.
Offer. So, but yes, we are developing an ammonia sensor. So hold that thought. Those that know me know that I've published on ammonia a couple of times. We do have a method. We've got a nice, slightly more robust way of doing it in the company. That'll be coming soon. And was the other one phosphate?
Phosphate, yeah, ammonium.
Yeah.
It was a method reference. I don't know if that was a related question. What is the method reference for ammonium and phosphate?
Yeah, so for phosphate, we would use the NIST or the CANSO standards and our typical benchmarking with a standard auto-analyzer, benchtop auto-analyzer itself, calibrated to those standards. So that would be our standard reference measurements for those.
For sure. So it's also worth to mention, so it's phosphate, nitrate, nitrite, silicate, which is also should be important to some people, dissolved iron, and high accuracy pH are the current commercial available parameters. And we're really pushing for ammonium, and it's on its way, right, Matt?
It's way, yeah.
Okay, there's a few more down here for more questions here. So did we get our limit of detection for phosphate in micro milligrams per liter? Did we get that answered? It looks like.
I don't think we did answer it. I've done a quick calculation. I'd like to check it and double check my quick maths, but I think we're down into the about 2 micrograms per liter as phosphate. So 0.0015-ish milligrams per litre. So it's very low limits of detection in comparison to most riverine and in terrestrial water limits.
Okay, yeah, so yeah, Brian kind of said agreed, Brian, and he said since there's a version with a higher detection range of 0.62 micrograms per liter or 620 micrograms per liter, what would be the detection limit for that one for the higher detection range?
So that's a very good question. I'm not sure I know the answer to that, but I think your detection range falls off the limit of detection falls off a little bit. I would expect that to be about double, so somewhere around the 3 micrograms per litre. Alex, do you want to add to that?
Yeah, I don't know exactly so that sensor's the higher range is still in the sort of R&D phase here at ClearWater Sensors. So what we sell is the 0 to 10 micromolar, the 0.3 milligrams per litre P. But for the up to 0.6, we're doing some sort of internal testing on that, but I don't have the numbers on the LOD at the moment.
Okay, so we might have to get back because Todd Howell,
Yeah.
who I know pretty confident works in freshwater. He asked if the if the range is 0.05 micromolar for phosphate. Maybe get back to him on that one.
Yeah, so that one, so that is right at the detection limit. So you're not going to, because it's the detection limit, you're not necessarily going to be able to measure confidently. You can't put a number on it, but about 3 times that detection limit is where you would be able to say, yes, this is this is the concentration, because that's the limit of quantification. So you'd be looking at sort of about 0.15 as sort of being able to, at the point of being able to say, yes, that's the concentration, but you will get a value. It'll be, it'll be noisier, and you'll have less confidence in it at that sort of level. Do you want to add anything?
Yeah, no, it's just the standard metrology. That's 3 times the standard deviation of the measurement at that low concentration. So that's where you get that limit of detection. Yeah, so that's 0.05 micromoles, which works out as being 1.5-ish micrograms per liter, 0.00015 milligrams per liter as phosphate.
Yes. Yeah. Good. Okay. So I know there's lots of questions around accuracy and that when you start getting into the 0 to 20 micrograms per liter high accuracy ones. So we'll be willing to work with this is kind of the partners that we're willing to work with to test these in some of the environments. So that would be great if anybody has a calling. Okay.
Yeah, it'd be good to sort of hear about how much sort of demand there is as well in the sort of customer base for that higher range. Because at the moment we're selling our standard product as the 0 to 10. Do we, is there what is the demand for the high concentration range? I know there is one, and that's why we're doing R&D on it. But it'd be interesting to see how many. Please shout if that's a particular
or at least
interest.
put up your hands. Yeah. Put up your hands virtually and say who would be interested in something like that.